So our talk this morning bears a Darwinian title of Emergent Design and Evolutionary Architecture. And our expert in the field is Neil Ford. Neil's a software architect with ThoughtWorks and a self-proclaimed meme wrangler. I'll have him explain that to you later because I'm not sure I understand it myself. He's also the designer and developer of applications, instructional materials, magazine articles, courseware, DVD presentations, and is the author and or editor of over 6 books spanning a variety of topics including 97 Things Every Software Architect Should Know, and his most recent work, The Productive Programmer. He specialises in the designing and building of large-scale enterprise applications and has done so in many technology sets and across diverse business domains. He's also an internationally acclaimed speaker, having spoken at over 200 conferences and delivered over 2,000 talks. Last year alone, Neil spoke at over 50 conferences around the world. But it's not all about theory. He balances that speaking circuit with around half of his time in billable project work. And this ensures that the ideas that he's here to talk about are founded in practicality and directly relate to what he sees working and not working in the field. Now, given his hectic speaking schedule, Neil's also clearly a pretty hardy soul. When he left his home in Atlanta last week, it was 31 degrees Fahrenheit. After enduring a 31-hour flight, or a 31-hour travel, multiple flights, he arrived in Brisbane to 31 degrees Celsius, where we had him present to a packed room with no air conditioning. So he got through that birth of fire well and seems to have maintained his sense of humour in the process, and so for that he's to be congratulated. Now, we will have time for questions at the end of the session, so I'd ask you please if you could hold them until then. But for now, will you please join me in welcoming Neil?
Thanks, Chris. One of the questions that frequently comes up when people see my business card is this title, Meme Wrangler. ThoughtWorks, for better or for worse, lets you choose your own title. And the first set of business cards that I got from ThoughtWorks had application architect on it before I realized that in a lot of places, especially in the US, application architect means post-useful. It means you spend more time in Visio than you do looking at source code, which is a bad thing. And the rule in ThoughtWorks is you get one set of business cards with a title on it, and once you use those up, you can get another set, and you can change your title if you want. So the second set of business cards that I got, I invented the title Meme Wrangler. And for those of you unfamiliar, a meme is the sociology term for unit of thought. It's kind of like a virus, but it's a thought. So a meme is to a thought as gene is to DNA. So a meme wrangler, someone who kind of wrangles the atomic parts of thought, which is kind of a cool hippie title. And it usually has an effect. If you hand someone a business card that says Meme Wrangler on it, they either go, ooh, that's cool, or what does that mean? And so the third set of business cards I created, I compromised with Software Architect and Meme Wrangler, and that seems to have struck the correct balance. And I am going to be wrangling memes this morning around emergent design and evolutionary architecture. This is a subject that I've done a lot of R&D on over the last year or so. In fact, this talk has a symbiotic relationship to an article series that I'm writing for IBM Developer Works. It's on their site that has the same name, Evolutionary Architecture and Emergent Design, which is really about the way that we think about architecture in agile projects. And you can read this series. It's you don't have to have a subscription or anything silly like that to IBM Developer Works. You can type in this hideous URL, but life's too short for that. So I've created a trimmed version of this. That's the table of contents for these articles. There are 10 of them up there now, and I'm continuing this series this year, so there'll be more to come as we go along. What I'm talking about this morning is, in fact, this idea of emergent design and evolutionary architecture in software. And here's a mind map of the things I'm going to talk about by way of agenda. I'm going to talk about a few kind of overarching concerns, things that you should think about when you're thinking about design and architecture in software. And then I'll spend a fair amount of time talking about design, a bit of time about architecture, and then wrap up with some closing thoughts on this subject. So having said that, let's talk about what I'm calling a prelude which are really kind of overarching things to think about when you're thinking about design in software. The first thing you'll probably notice in this talk is this divergence of title. The original version of this talk was going to be called Emergent Design and Architecture. And I was chatting with one of my enterprise architect friends, colleagues at ThoughtWorks, and she convinced me that emergent architecture is a really bad idea. You really need evolutionary architecture because you have to have something to build everything else on. The architecture is something that is there, that is the foundation for all the other stuff that goes on top of it, but it can evolve. But you have to have one in place before you can even start. Design is much more malleable. You can start with very little design and end up making pretty significant changes to it along the way. And there's this distinction between design and emergence and architecture and evolution. And as I talk about design, that should become more apparent. I should, of course, define my terms. When I say emergent, the Webster definition is rising or emerging out of something that covers or conceals, issuing or coming to light, or something that arises unexpectedly, calling for prompt action or urgent. That, in a lot of ways, is like design in software. Design in software is really tricky because you don't know what you don't know. Software is very, very highly coupled. Even though we work hard and we have a lot of techniques for decoupling things, software is still extraordinarily coupled, much more so than physical things in the real world. Meaning that a small change to this can have an impact way over here in something that seems completely unrelated, but they are because everything is coupled to everything else. And this idea of emergent design is do as little design as you can get by with until you get far enough into the problem to understand what you didn't know when you started. And if you can do that, if you can walk that fine line between not doing too much, doing just enough along the way, you can evolve and emerge a design and start seeing design elements out of code. And I'll show you a concrete example of that in just a second. This is a spectrum. It's not a binary proposition. You're not either emergent or not. There's a spectrum of design in software that goes all the way from the left of this kind of almost straw man, pure waterfall approach of a bunch of ivory tower architects who spend all their time in Visio and they come up with some sort of elaborate design and drop it through a hole in the floor to hapless developers who are required to implement it with no changes whatsoever. We're pretty sure that doesn't work well in software, almost ever. And then on the far right-hand side, you have this kind of cowboy hacking that you did when you were 17 years old, where you kind of hack it till it works, and then when you want to change it, you hack it some more until it works, which works okay as long as you can keep the whole thing in your head, but as soon as it gets too big to do that, it's much harder to do. Where I'm trying to hit is somewhere along this spectrum, and emergent design is somewhere a little closer to the right than to the left. And it really depends on what kind of organization you're in as to where you fall on the spectrum. I was talking to someone not too long ago, and they said, yeah, we do iterative development, and our iterations are 2 years long each. And I said, you're not really doing iterative development. You're just doing lip service to doing iterative development. Then I asked them, what is it that you do? And they said, we build software for the space shuttle. I said, you know what? A 2-year iteration is probably pretty good for you guys, because they have constraints that most software projects don't. Literally, people will die if they get it wrong, and so they are willing to freeze requirements and work on things for vast amounts of time to make sure that they get it right. But that doesn't work well in a lot of businesses because one of the defining characteristics of business is forward motion and change all the time. This big design up front idea in software has been surprisingly resilient in the face of counter evidence. And everyone's familiar with this kind of big design up front mentality where you spend a lot of time in doing project planning and estimation, which leads to requirements and then use cases and functional specs and then design and then a big long series of coding and then testing and then fixing and integrating and fixing and integrating. This doesn't work particularly well in software because it doesn't leverage some of the strengths and weaknesses of software very well. And I'll just give you one example of that. I could spend the entire hour explaining reasons why this doesn't work particularly well in software, but let me just give you a quick example. This is a photo that my wife took. This is of a seashell and some seaweed on the beach somewhere. Let's say that arbitrarily this had 2 million pixels in it. And let's say that you had to create a version of this that had 200,000 pixels in it. And moreover, you had to take that 200,000 pixel version of this picture and hand it to someone and have them recreate the 2 million pixel version of it. How close do you think they would get to this image? They'd get the general shapes right and some of the colors, but there'd be a lot of really bad jagged edges because they're having to invent information to rehydrate it back to 2 million pixels. This is exactly like requirements gathering in traditional software projects. It's a lossy compression algorithm because you're trying to take this big, complex, nuanced problem and reduce it by compressing it by losing information. And then you're handing that to someone who's never seen the original problem and telling them to rehydrate it back up to the original idea. Well, they're going to have to invent stuff along the way, and you're going to have a lot of jagged edges and a lot of things that don't look quite right to the people who had the original picture in their head. This doesn't work particularly well in software, which is not too surprising. What's surprising to me is who thought this was a good idea in software? Well, it turns out metaphorically it kind of works because we have a hard time explaining what we do. When you talk to your grandmother, what do you tell her that you do? Well, I'm an enterprise architect. I worry about SLAs for big enterprise systems, and I manage server farms. And she's going to go, what? And you say, I'm in software. Oh, okay. That's what you do. We always try to talk in metaphors. We talk about bridge building. There are examples of emergent design out in the hard physical world, and this is one of my favorite examples, the evolution of this iconic user interface on the iPod. The first version of the iPod had the click wheel with buttons along the perimeter and a button in the center, and then the scrolling wheel to get to songs. The second generation that came out, they got rid of some moving parts, made this more of a membrane with buttons along the top. But then when the first iPod mini came out, they didn't have room for this row of buttons, and so they ended up making this, which is the design that has now existed for all the subsequent generations of iPod. So they didn't get it right the first time either. Usage showed them a better way to build it with fewer number of moving parts and still have the same kind of capabilities that it had before. And this is just like software. The difference is that Steve Jobs doesn't sneak into your house when a new version of the iPod comes out and replaces your old one with a new one, but we can do that in the software world because everything is soft. We can make changes to things after they've shipped and been sent away. What does emergent design mean in software? Well, emergent design in software really is the ability to look at this and stare at it and think about it long enough until it finally resolves itself into something that makes sense and something that is repeatable. So a lot of emergent design in software is really about discovering and harvesting abstractions and patterns in existing code. Let me talk about that for a second. Now, when I'm talking about patterns here, I'm not talking about the official gang of 4 design patterns, elements of reusable object-oriented software kinds of patterns, which are very useful things. That is a catalog of the kinds of patterns that appear in all kinds of software. Those are patterns with a capital P. What I'm talking about are patterns with a lowercase p. And what I'm calling in this talk and this article series, idiomatic patterns. It is my contention that every piece of software has idiomatic patterns in it, which are ways of solving particular problems that work well for this application or for this enterprise. For example, you probably have a common way of handling security in all of your applications across your enterprise that's a little bit different than the way other enterprises handle security because of external constraints that you have. That's an idiomatic pattern within your enterprise of how we handle security. And just like other patterns, these idiomatic patterns are, as much as anything else, nomenclature. It's a way of talking about patterns and common abstractions. Without having to explain the entire thing every time, you can assign a name to it, and it makes sense for those who are working with that pattern. And there are two types of patterns: technical patterns, which are plumbing kinds of ways that we do things. Here's how we handle transactions within our organization. And there are domain patterns, which describe the kinds of business processes that we use, because you have common business processes that go between applications across the entire enterprise as well. Patterns describe effective abstractions, things that have worked well here, ways that we want to emblazon how we do things into code, and so you will continue doing that because it works particularly well for this organization. And a lot of emergent design is identifying these patterns. But one of the hazards in software is trying to abstract too early, because it's really then just speculation without facts. It's very easy to say, well, I see how one of these works. I'm going to build a framework that assumes that they're all going to work like this. And then when you get into more cases, you realize that the framework doesn't quite fit all of those things. You're trying to create that abstraction too early, which means you either have to rework it or you spend an enormous amount of effort trying to hammer other things into something that are not quite effective, or the ways that you should be doing those. In the Agile world, we try to kind of counter this with this phrase, Yagni. You ain't going to need it. If you're ever pairing with someone and they say the words, ooh, I think I'm going to build a framework for this, you're supposed to smack them and say, nope, we don't need that yet. Eventually, if we need that, we'll harvest that framework from working code, but let's just do what we need to do right now because we don't know enough to make that evaluation yet. This is important in the kind of software that we typically build because business processes change radically and often. In fact, business processes can change much faster than we can put those things in software. Because you can have a meeting for a day and change the entire direction of the business, or merge with another company. Software is always playing catch up to what the business needs to do. And so if you really want to be effective at building business software, you have to find a way to try to lessen that gap so that they don't completely sprint away from you, or even worse, IT becomes a governor on business innovation, which is bad because if your competitor doesn't have the same governor you have, you are eventually going to lose. So how do you know when to abstract things? Well, I don't know. Experience helps. I think that's one of the reasons that this title of architect exists in so many software organizations. I think what architect really means is I've seen enough good and particularly bad software to know the good when I see it, but it's really hard for me to explain what that is. If you believe Malcolm Gladwell in Outliers, he suggests that it takes 10,000 hours of dedicated work to become an expert on something. And that expertise is virtually impossible to explain to someone because it becomes innate. And that's a lot of what architects become, is I've seen enough bad code to know it when I see it. And I know to avoid it when I can. Okay, well that's enough of this prelude stuff. Let's talk about design, and specifically emergent design. The question I would really like to answer is this one. What is software design? Fortunately, someone has already answered this for us. There's an essay written by Jack Reeves in the fall of 1992 in C++ Journal called What is Software Design? It's still available online, and it's worth reading because you would swear it was written yesterday, which just goes to show that we have a hard time learning from the past in the software world. And what Jack Reeves does in this essay is try to compare traditional engineering to software engineering. The goal being, let's see if we can remove the double ticks around engineering and make it a real engineering discipline. And when you start comparing those things apples to apples, some interesting revelations come out. One of which is the final goal of any engineering activity is some type of documentation. If you're a civil engineer and you are tasked to design a bridge, what is your final deliverable? Is it the bridge? No. Somebody else builds the bridge. Your final deliverable is a design to use to build a bridge. So it's a type of documentation. When the design is complete, you turn it over to manufacturing. And the manufacturing team with some input from you as the original designer, should be able to construct the entire thing. So if you're doing an apples-to-apples comparison between traditional engineering and software engineering, what is the design document in software? Is it the UML diagrams and the napkin sketches and the whiteboard doodles and sequence diagrams and all that stuff? It is, but is that sufficient to manufacture the finished product? It's not. It's preliminary. The final design document, the final deliverable in software, is the completed source code. In software, the design is the completed source code. And this is where the manufacturing metaphors start to break down in software, because software is cheap to build. It doesn't even qualify as inexpensive. It's so cheap that it's essentially free. Now, remember, Jack Reeves wrote this in 1992, and he was enduring C++ compiled link cycles, which are very long. If you're in the Java and the .NET world today, every time you stop typing, a group of elves comes together inside your machine and instantly manufactures your design for you in the background without you even realizing it. It's so cheap now, you don't even think about it as a separate stage. It just happens every time you stop typing. So it's incredibly cheap, because manufacturing is the build process. Reeves goes on to say that software design is easy to create in the mechanical sense, because you're just typing highly structured prose that gets graded by a compiler. But then his conclusion is that given that the software designs are relatively easy to turn out and essentially free to build, an unsurprising revelation is that software designs intend to be incredibly large and complex. I would maintain that software designs are probably the most complex artifact that humans build, because everything is coupled to everything else. And every time we kind of get a handle on what it needs to do, we up the game. Client server, we learn how to do client server. Now we need to do distributed computing. We learn how to do that. Now there's web computing. And you get the web stuff down, and now there's AJAX and interaction. The problem changes faster than we can ever get a handle on it. And what we tend to build are these incredibly large, complex, and extremely coupled things, and it's no wonder that it's so hard to deal with these things. In software, it's cheaper and simpler just to build it and test it than do anything else, which I think suggests that we probably will never have the same level of mathematical rigor in software that they do in traditional engineering. Because part of the mathematical rigor they have when they build bridges is predictability. I need to know, if I build this bridge, will it stand up under stress or not? In the software world, we're at where the bridge builders were when they would build a bridge and roll something heavy on it, it would collapse, and they go, that's kind of a crappy bridge, let's try again. That's about the level of engineering we have in software. But we have advantages over traditional engineers in that it's incredibly cheap to build it and just test it and see if it does what we think it does. Can you imagine what bridges would look like if civil engineers could instantly manufacture a bridge on the site and play what-if games with it? It would make the things in the Jetsons look like the things from the Flintstones. We would have these enormously elaborate, complicated bridges, and we'd have bridge engineers going, that looks okay. Let's see what it would look like if it were 2 feet over further this way. Let's add another deck and see what that would look like. Let's add a curlicue at the top and see what that would look like. But it's hard for them to do that. The overwhelming problem with software is that everything is part of the design process. Coding is design, testing is, and debugging is design. And what we typically call software design is still part of the design process. So it may be cheap to build, but it's incredibly expensive to design. Meaning that if you design it and get it wrong, you're dealing in the most expensive medium there is in software, which is where emergent design comes in. Because emergent design is really about discovering design in code that already does something useful and being able to harvest that and find effective abstractions so that you can reuse those abstractions in multiple places because they fit well with either a technical problem that you're trying to solve and you want it to be consistent across your organization, or there's a problem domain abstraction. One of the huge goals in software is reuse. But the problem is velocity, getting stuff done, and building reusable things are opposing forces. You can't get good velocity to try to keep up with the business and build reusable things at the same time. But what you can do is go at full velocity and look backwards and harvest the things that work particularly well. That's emergent design, and that's the ability to harvest idiomatic patterns. I'm going to talk about things that make that easier, but first I'm going to talk about the much bigger problem with emergent design, and that are things that obscure emergent design and make it hard, because our world is rife with these things. And the first of these I'll talk about is complexity. There are two kinds of complexity in software. There is essential complexity, which is the inherent complexity of the problem. Every problem has an inherent complexity, which is just what it takes to solve that problem. But we also have accidental complexity, which are all the interesting ways that we've accidentally made things more complicated than they need to be. For example, let's say that you want to do a mail merge from a database to produce a form letter. That's the essential complexity. But in your reality, it's like, well, the customer data comes from the mainframe and the sales data comes from this client-server application, so we need to merge them together in the data warehouse and do a transformation on it before we can get into this intermediate data format before we can do the mail merge. That's the accidental complexity part of it. So when you look at a problem within your organization, think to yourself, how much of this is essential and how much is accidental? This is also a spectrum. And here are a few examples that I've encountered, my colleagues and I, during our work in this space. And the first of these is hunting season. We built an application once that was for an auto manufacturer in the US, and they had plants scattered all over the US. There was one really good union representative who got a special deal for one of the manufacturing plants. I remember it was Grand Rapids, Michigan, because I can't forget that now because I spent so much time thinking about that problem. What their union rep did was got a special part of the contract that said every employee of that particular manufacturing plant got the first day of hunting season off as a paid holiday. He's just a really good union rep. But now we had to write HR software, and everywhere in the HR software we had to have these special cases for this one manufacturing facility because it changes vacation accrual, it changes pay calculations, it changes everything. And as software developers, we would love to have gone to that union rep and said, yeah, you know what? No, you can't have that extra day. It's just making our job too complicated. We couldn't. It was the essential complexity of the problem. And so we had to suck it up and do it. A little further on the spectrum toward the right is something that every user thinks they want until they see it, which is field level security. Part of the problem in software is when you ask users what they want, they're imagining stuff. They've never really seen it, but they can kind of imagine what they think it might look like. And I can't tell you how many applications I've worked on where it's a hard requirement that we have to control the visibility and the accessibility of every single field on this form. So you build up all this infrastructure to do that, and you finally sit down with the users and show them how they configure all that, and they say, wow, that's really complicated. I don't want to have to do that for every single page. It's like, you think that's complicated? You should see all the stuff underneath that makes that possible. It's unbelievably complicated, and they always end up saying, you know what, we'll just lock it down at the page level, and that'll be fine. And you end up throwing away all this elaborate code that you've written, because what they imagined is not the reality of what they saw. And then at the far right end of the spectrum, you get things like EJB and BizTalk, which are not inherently bad ideas, but the way most people apply them make them bad ideas. If you really built a pet store using enterprise Java beans, I would beat you to death. Because there's no way that you would use that solution for that problem. But this is part of the problem in software when you're trying to do big design up front, because you don't know what you don't know. And so the tendency is to say, well, we don't really know what this requirement is going to be, so let's over-engineer it and we'll buy the biggest, most complicated thing we can find just in case we need all that extra power. But the problem is you pay in terms of complexity from day one, whether you end up using all that extra power or not. But there's always this fear that you don't know what you don't know, and so you think the conservative approach is to overbuy and overcomplicate things early, but it just makes things hard as you try to move forward. The second thing that makes emergent design hard is technical debt. This is a great metaphor that Ward Cunningham came up with a few years ago, and this metaphor works really nicely in software. The idea of technical debt is when you think about the good, clean, perfect design that you could create if you had all the time in the world to get it right, you take that and then the thing that you're actually working on when you go back to work today, and the delta between those two things is technical debt. It's all the compromises you've made along the way because of external pressure like schedule pressure, or there's a particular tool or framework you have to use because it was really expensive and your CIO went on a golf outing and had to buy that thing, so now you have to use it whether it's suitable or not. Those are all things that contribute to technical debt. And the thing that makes this metaphor so nice is you can really think about it the way you think about credit card debt, where you have principal and interest. And of course, when you have a credit card and you have a high credit balance on it, when you get more money, you can't spend all that money and even pay back the principal because some of that goes toward interest. And you can think about pretty much any project as a combination of principal and interest of how much technical debt we have accrued on this particular project. Where on software projects, interest is time. When you have a set of time to build new features, you end up spending some of that time working through the compromises that you were forced to impose on your software earlier. And a lot of organizations build up to the point where the interest payment equals the amount of time that they have. And so they make no forward progress whatsoever because they're doing nothing but trying to pay the interest on the technical debt. Technical debt is a reality of the software world. We're never going to get away from it. The real trick in software is not avoiding technical debt, it's negotiating repayment. Wouldn't you love to tell your project managers when they come and say, we need these new features, you're like, nope, I'm sorry, your credit limit is all used up. You can talk to one of our representatives and maybe we can give you a temporary extension of your credit, but that's going to mean more interest payments in the future and you really need to pay some of this down or you're going to have to declare software bankruptcy on this project. But the trick here is first you've got to convince someone that technical debt exists, and then you can start a conversation about repayment. And it has been our experience that demonstration trumps discussion. It's one thing to go to your non-technical manager and say, you know what, I feel sick inside, I can't sleep at night, I think our software might be starting to suck. It's a really hard argument to win because they're going to say, well, do you have proof of this suckage? And it's like, well, no, but you know, I kind of feel bad about it. But there are some convincing metrics you can use. And here's one that was produced by one of my colleagues, Eric Dernenberg, who's local here in Australia now. This is when he was working on a project in the UK. This is a big public-facing media site. This is the metric cyclomatic complexity per line of code. That's the red line. This is from April 1st, 2006 to August 18th, 2007, with the public releases of this site overlaid in gray numbers. Just by looking at this chart, can you tell me what the first public go-live release of this site was? It's number 3. Because you can see all the volatility as they had schedule pressure early on. It was making for more complicated code than it needed to be, and it reached a local maximum right there. And they made their ship date, and Eric took this part of the diagram, it was all that existed at the time, to the project manager and said, look, we did a lot of work to get to this deadline, but we incurred technical debt, and we need to pay some of that back, or we're going to spend a lot of time paying it back for everything that we do. And release 3.0 and 3.1 of this software project was mostly just cleaning up technical debt. And the inertia of that effort means this is a much smoother line, and it bottomed out about here. Right after release 7, the client decided we want more features faster. So they started a separate work stream. So now you have 2 teams working on the same site, and because of integration, the technical debt, the complexity started creeping up again very slowly and in a much more controlled way. But this is a decision the business gets to make. Are you willing to incur a little bit of extra complexity, meaning that you get a little less velocity per team so that you can get more features faster by having 2 teams working on it? You can assign a dollar figure to the delta between here and here, and the business gets to decide, is that a good use of our money? Because if we have more features, we get more users and more money, etc. Demonstration trumps argument for things like this, and this is a good example of a nice visual for technical debt. So technical debt's the second thing that makes emergent design hard. The third thing is rampant genericness. Genericness is usually viewed as a kind of a good thing in software, but the problem is you have too many software systems where they say if we build lots of layers for extension, we can easily build more onto it later. The problem with that approach, though, the problem with these exuberantly layered architectures is that it increases the overall complexity of the entire thing. And you have to pay for that complexity from day one, which is really just a form of accidental complexity or generic obfuscation. Because if finding idiomatic patterns is hard in a code base, it's much harder if you split that functionality into 2 layers. And if you split it into 3 layers and 4 layers, it takes much more expertise to be able to see that these 4 things are really part of the same idiomatic domain pattern, and we should try to encapsulate those things and do other things the same way. It's very hard to see through those layers like that. This is a diagram that I harvested from the internet for the state of New Mexico's vision and mission. I'm sure the state of New Mexico has a lot of hard problems, but really, you really need all these layers for stuff. Every time I show this to one of my colleagues, their first response is to roll their eyes because we see so many of these kind of diagrams in the enterprise world, these layers upon layers upon layers of things so that you can build more onto it later if you need to. And I've seen several software projects that were so generic they failed to deliver a single bit of functionality before they were shut down because they were so complicated they couldn't get anything done. I was working on a project not too long ago that we were brought in to help fix that was supposed to take a year. It had just had its 4th birthday, and they still hadn't delivered any code. It was marvelously generic. You could do almost anything with it except get it to do one thing, which it never did until we stripped away a bunch of these layers and stuff and said, let's get it to do one thing first, and then we'll think about getting it to do other stuff. Well, that's all ranting about what makes it hard. Let's talk about things that make it easy. And one of those things is test-driven design. Usually when you see the letters TDD, it's test-driven development. But if you're really adamant about doing test-first development, it helps the overall design of your code because the design will emerge from tests. Because you get an atomic understanding of intent, and you tend to build better abstractions with less accidental complexity. So here's another tortured metaphor. You think of a bridge like the Sydney Harbor Bridge. And I have no idea how many rivets are in the Sydney Harbor Bridge. I know the Golden Gate Bridge in San Francisco has more than 1 million rivets in it. You can bet that the engineers who study the structural characteristics of that bridge, that they know the exact stress capabilities of each one of those rivets, and they are able to say 1 million times that number tells me something about the overall stress characteristics of that bridge. But we don't have the same regularity of components in software. We may have 1 million parts in a piece of software, but they're all completely different. You can't say 1 million times something tells me something. You have to say this plus this plus this plus this plus this 1 million times, and that's not a good use of your time. But what tests let you do is look at those things in isolation and understand what they really do and have some gleaning of them at the smallest possible level. Now, in the article series, I do a case study where I illustrate this for the simple problem, which is finding perfect numbers. A perfect number is where the sum of the factors equals the number. 6 is a perfect number because if you look at the factors of 6, they're 1, 2, and 3, and if you add 1 plus 2 plus 3, it equals 6. So it's a simple little math problem. The mathematical definition is the sum of the factors minus the number equals the number, because the number itself is one of its factors. And what I did was built this in 2 different ways. I built it just by writing code and then writing unit tests for it, but then I derived the solution by doing it test first, where I took every little piece and built it from the bottom up rather than the top down. And you can read and see the entire source code for that, but I'm going to show you the results. When I was finished, I ran the cyclomatic complexity on those 2 solutions. And the cyclomatic complexity for the test after version, it had an average of 13 lines of code. There was one method that had 13 lines of code, and its cyclomatic complexity was 5. For the test-driven version, I had a lot more little tiny methods because I built them all from the ground up. The average length of lines of code per method were 3.56, and the average cyclomatic complexity was 1.56. Even in this really tiny problem, the TDD version was 3 times simpler than the test after version. And these numbers hold up as you scale up bigger and bigger and bigger. TDD tends to give you better designs because you think about every little component that goes into the bigger piece. Test after doesn't expose design flaws as early. TDD forces you to think about every little thing and encourages refactoring what's not right. And that's the second part of emergent design, is the ability to do refactoring. If you find abstractions in your code, you need to be able to refactor toward those abstractions in other places. And one of the things that you really need to be able to do refactoring with confidence is some unit tests, so that you know that you're not breaking something. Because software is so coupled, you can usually determine the localized breakages, but then this breakage that happens 2,000 lines of code away is really hard to predict because everything is so coupled to everything else. The other thing you need is collective code ownership. It's bad on projects when you say, well, that's really not quite right, but that's Bob's code, and Bob gets really irritated when you touch his code, so I'd better stay away from it. That's a bad attitude to have, because anybody should be able to change anything anytime. I gave this talk to one group of people, and this guy said that in his organization, if you ever touch some code, you become the new owner for it, and so nobody ever touches anything. And I said, I bet your software is incredibly brittle in it. And he said, you have no idea. You change one variable name somewhere and the entire house of cards just come crashing down, so they never touch anything. They're terrified of their code base. One of the ways that we try to enforce this within ThoughtWorks is most of our projects we do pair programming. So it's a pair that's creating every piece of code all the time anyway, and we do pair rotation, so every person sees every part of the code base, and there is no single owner for anything. You really need this collective code ownership because you are jointly designing whatever it is that you're building. Because the source code is the design and software, and you're all collaborating on the design in real time all the time. And you need to do that collectively. You also need to fix broken windows whenever you see them. This is a metaphor that comes from the Pragmatic Programmer book. It's based on a study that they did that if you have an abandoned building, usually nobody will bother it until the first window is broken. And then almost immediately all the other windows will be broken and graffiti will sprout on it because that first broken window indicates that nobody cares. You see this in source code all the time. It's those little things that are not quite bugs, but they're quite right. And you go, well, I'm not going to bother fixing that because it's not technically a bug. This is exactly why so much software is deployed like you deploy a hand grenade, where you deploy it and you pull the pin and you carefully walk back from it because you're afraid it's going to explode into 1,000 pieces at any moment. Because it's really fragile, because there are hundreds or thousands of little design compromises all through it. There's this idea in the software world that as software gets bigger and older, it gets more brittle and more fragile. And I don't think that's true. I've seen code bases that get stronger with age because there is a desire to fix obsolescent abstraction. And this sounds like an oxymoron, but you should prudently refactor aggressively. Meaning that if you see a little flaw, you won't go off into a multi-day refactoring binge just to fix that thing. But if it's a small thing, it's 15 or 20 minutes, you tend to just fix it in line with your regular work. And if it's something bigger, we tend to build a technical debt backlog, which is a place that you can go. If you finish a card early and you've got some time, you can go to that technical debt backlog and start hacking away at those things. And if you have a lot of technical debt, you can assign developers each iteration to do nothing but hack away at the technical debt and gradually increase the strength and flexibility of your code base, because code should get stronger with age. So I've been doing a lot of hand waving about this stuff. Let me show you a concrete example of this idea of emergent design and why it's so important in software. And before I do this, I need to talk about a couple of simple metrics. These are well-known code metrics. One is cyclomatic complexity, which has been around since the 70s. Thomas McCabe created this metric. It's really a way to measure, numerically measure how complicated a function or a method is by measuring the number of paths and branches through a method or function. The formula is edges minus nodes plus 2, where nodes are lines of code and edges are paths through code. So if you look at this little method in either Java or C#, if you kind of flow chart this out, the nodes are the lines of code and the edges are the paths through the code. In this particular case, we have 4 edges and 4 nodes. 4 minus 4 is 0 plus 2. The cyclomatic complexity of this method is 2. But it's kind of boring when it cancels each other out like that. So let's look at a slightly more complicated version. This one has several different decision statements, and if you draw this out painstakingly in this flowchart view and then label all this stuff, you see 8 edges minus 7 nodes plus 2. Cyclomatic complexity of this particular method is 3. This is a way to do apples-to-apples comparison, because if you have a method that's a cyclomatic complexity of 20 and one that's a cyclomatic complexity of 5, you can say that this one is a lot more complicated than this one. And it may seem like that's enough, that if you're really trying to hack at the most complicated parts of your code base, you just look at the cyclomatic complexity and go attack that. But there's slightly more nuance than that, and this other metric that I want to talk about is afferent coupling. Afferent coupling is the sum of how many other classes use this class. It's the number of incoming references to this particular class. If you look at a code base and you count every class that uses this class, that is its afferent coupling. This helps you determine the hard, crunchy center of your code base. And you can measure this with a bunch of tools. There's a tool called CKJM that helps you measure this in the Java world. There are tools like Independ that help you measure this in the .NET world. This is a very well-known metric. And so what I decided to do is take this combination of metrics and apply it to an existing open source code base that I had not done any work on previously. So I applied these metrics to struts, which is a very well-known web framework in the Java world. And here are the results. Now, if you just look at cyclomatic complexity, this WMC number is the weighted cyclomatic complexity, which is the sum of the cyclomatic complexity of every method in this class. You just add up the cyclomatic complexity for all these methods. And if you look at these, it looks like this double list UI bean has a 66, which is the most complicated class in the struts code base. But then you look across, and it's only used by 3 other classes. You could spend an enormous amount of effort trying to clean up double list UI bean, and it really only benefits 3 other classes. What if you sort these by afferent coupling? You'll see that the champion here, because it's a component-based web framework, is component with 177, but it's not that complicated. What I'm really interested in here are high combinations, like this UI bean guy, which has a complexity of 53, and it's used by 22 other classes. That's the one that I'm really curious about, so I started poking around in that UI bean class, and I discovered that the most complicated method by far was this one called evaluate parameters. I keep meaning to add Jeopardy music to this, but this is what this method looks like. Big, long, ugly method, but if you'll notice, there's a lot of kind of similar code in it early on. And I started poking around at some of the other classes that had high combinations, and I realized that the thing that was making them complicated were methods called either evaluate params or evaluate extra params. So I did a little bit of command line magic. I said, find me all the Java source files, and then in each one of those, search to see if there's a method signature called evaluate something params, and then stick that on my clipboard, and then I pasted. Every one of these classes has evaluate params or evaluate extra params in it. What this code does in the struts code base, struts automatically harvest some of the parameters that you send as part of the URL for its own use, but then it has to do something with the extra ones that the users might have sent. That's what evaluate extra params does. It turns out that is the most complicated part of the struts code base, is handling those extra params. There's no way when they started struts they ever could have anticipated that that would be the most complicated part of the code base. And yet it turns out to be the case. That's the real benefit of emergent design, because when you start designing something, you don't know what you don't know. You never would have predicted in a million years that the most complicated part was this thing that seemed like it was so simple. In fact, one of the struts committers, after I wrote this article about this in the Developer Work series, contacted me and said that he had independently kind of discovered the exact same thing, and what he ended up doing was creating a framework within struts to handle parameter stuff, and ended up removing a huge amount of the complexity of the code base because he understood that was a first-class design element for the first time. They weren't just handling it on an ad hoc basis. Now, there is a way to fix that locally by using some advanced language features like reflection. Here's an example of fixing a lot of those repeated bits of code using reflection. And I'm not going to go into this. You can look at that in the article series if you're curious. But just by doing this little part, each one of those little repeated blocks was 3 lines of code, and there were 22 of them. That's 66 lines of code. I fixed it with a 9-line method that used reflection, and I was able to reduce 57 lines of obscuring duplication in the code and lower the cyclomatic complexity by 21 points just by this simple change. So that's a good example of the kinds of things that you end up discovering when you start going on these hunting expeditions for emergent design. And there's one last aspect of emergent design that I'll talk about, and that's the expressiveness of computer languages. Because if code is design, readable design matters. And complex languages hurt readability. I defy anybody in this room to be able to find an idiomatic pattern in an assembly language code base, because there's just so much details about assembly language that it's really hard to see the abstractions. And most comments don't help that much because they're not executable, meaning that there's nothing that forces you to change them, which means they're always potentially out of date. Have you noticed that your IDE has realized how useless comments are? What does your IDE do to comments now? It grays them out and puts them in italics. It's like your IDE is telling you, I know you've written this one time, you're never going to read it again, so I'm just going to kind of hide it from you. In fact, a lot of IDEs now make it so you can just collapse the comments away so you don't have to skip over them anymore. I think the next step in IDEs is just going to make them white on white and be done with it, because it realizes that they're not doing you any good. So here's an example of that, an idiomatic unit of work pattern. So let's say that within your organization you have a lot of e-commerce kind of stuff, and you end up with this kind of pattern where you set up some data infrastructure, you do some work, when everything's okay, you complete the transaction. If something goes bad, you roll it back and you clean it up. This is a good example of a technical idiomatic pattern. This is the kind of way that we want to handle this every time. And so you could use a formal gang of 4 design pattern, the command design pattern, to fix that. And this is what that would look like in Java. You send in a command, which are the things you actually want to get done, and then you complete, roll back, and clean up, etc. And now you can change that original method to this, which means that you basically create this new command, anonymous inner class, that just does the couple of things that you want to do. The problem, though, in Java, which is the kind of standard enterprise language around the world, requires a lot of crufty kind of stuff. Because what you really want is just wrap these things in a transaction. But Java forces you to put all this kind of obscure syntax with anonymous inner classes and curly braces and all that stuff in there, which makes it a little bit harder to read it and see what's going on. If you use a slightly more expressive version of Java, there's a dynamic language version of Java called Groovy. You can write the same pattern, but in Groovy, the command design pattern is already built into the language. And so this is what the wrap-in transaction command looks like. And then anything Groovy that's in curly braces like this is automatically something that's executable as a command. That's what we're passing in as a single parameter, and that's where it gets executed. And now that's a lot more readable, because now you've gotten rid of the obscuring code around it, and you can see closer to what you're trying to do. And there's another expressive language that runs on the JVM and the CLR, Ruby. It also runs as standalone, and you can do the same kind of stuff in it. where you can say wrap in transaction, do these things, and then the infrastructure handles that for you. There's one last thing I'll say about expressiveness, and that's about abstraction styles. Everybody here is familiar with imperative languages, which encompasses structured and modular languages and object-oriented languages. But you hear a lot of in the world today about functional languages. That's the new cool thing on the block. Languages like Scala and F# and Clojure, which all run on the standard runtimes that we have now. It's a really different abstraction style, meaning that some problems are going to be easier to express in a functional style than other problems. We're getting away from this idea that there's one golden hammer language that can solve every problem in the best way. But even within your language, you can think about expressiveness and abstraction in different ways. And a good example of that in an imperative language is an anti-object. The idea behind anti-objects is from this paper from Uppsala in 2006 called Collaborative Diffusion. And in this paper they say, the metaphor of object can go too far by making us try to model the real world too exactly. An anti-object is something that appears to do the opposite of what you think it should be doing. It's kind of like this. Is this a vase or is it two faces? Well, it really depends on your perspective. And I'm going to give you a really good example of this anti-object approach in the form of Pac-Man. I have to warn you, if you want to continue to play Pac-Man and enjoy it, you should leave now. Because I'm going to explain how it works, and after I do, it's not going to be as much fun anymore. When you think about the original Pac-Man console game that came out in the late 70s, early 80s, it had less processor power and memory than some watches have now. And they had a really hard problem to solve. How do you calculate the distance between two moving objects in a maze? They didn't have anywhere nearly enough processor power to do that. Now, if you were doing this today in a Java or C# or something like that, you'd create a Pac-Man object, you'd create ghost objects, you'd create cherry objects and all that sort of stuff, and then do that calculation. But they didn't have that luxury. They had constraints. And so what they did is model the entire thing as a state machine, and they built all the logic into the maze itself, not into the objects. The maze is basically just a big state machine where each cell has rules that it runs as it runs through. It just goes from left to right, top to bottom. And they invented this concept of Pac-Man smell. When Pac-Man is sitting on a cell, it has maximum Pac-Man smell, and the cell that he just vacated has maximum Pac-Man smell -1. And it decays really quickly, and all the ghosts do is wander around semi-randomly looking for Pac-Man smell, and anytime they encounter it, they go to the cell that has the next highest Pac-Man smell. They can move a little bit faster than Pac-Man. That's the whole game. Very, very simple, because they thought about the problem in the opposite way that you'd normally think about the problem. The reason this is going to ruin Pac-Man for you is the ghost can never cut Pac-Man off because they can't see him coming. They can only tell where he's been. So the only time they ever cut him off is if they just randomly happen to bump into him, because they can't see him coming. They can only chase him because that's the only indicator they have that he was around there is Pac-Man smell. Okay, I've been talking mostly about design. Let's talk a little bit about architecture. And you'll notice that, as I said in the beginning, architecture is an evolutionary process, a process by which something passes to a different stage, usually a more advanced or mature stage. And interestingly enough, architecture probably has more cogent stuff written about it in the world than software design does. And there are several different flavors of architecture out in the world in software. One is application architecture, which describes the coarse-grained pieces that compose an application. So this is a typical kind of architectural diagram that explains a message flow in a Model 2 web, a Model View Controller web application framework. You see a lot of diagrams like this. But in most of our world today, there's also this concept of a framework level architecture. When was the last time you downloaded a single class from the internet and used it in your project? You never do that. The unit of reuse in Java and C# is the library or the framework. And unfortunately, there's no good language support for this concept in the Java or the .NET world yet. There is an attempt in Java called the Java module system, but this is the problem with a messy democratic process. They got Maven guys and OSGI guys, and they couldn't agree on anything. They refused to compromise one iota toward the other direction, and so they ended up killing this JSR. But this was an important thing, so they recreated it in the form of the Super Package API, which is now called Jigsaw, and that will be in Java 7. We've retrofitted this in the Java world in tools like Ivy and Maven, which handle transitive dependencies for you, but we'll eventually be able to say at the language level, this application relies on this version of all these different frameworks. So now in the modern world, you say, I want a model view controller web application, and I'm going to implement that using these combination of frameworks. And then you have enterprise architecture, which concerns itself with how enterprises consume applications. And my favorite metaphor for that is that enterprise architects are kind of like city planners. They care about traffic flow and water flow and sewage and stuff like that. They don't really care that much about the individual characteristics of buildings. So if an application architect comes along and says, hey, I want 90% of the city's water supply because we're building a fountain on the roof, a city planner will say, no, you can't have 90% of the city's water supply. You get what everybody else gets. They're concerned about the overall landscape, whereas application architects are, in fact, concerning themselves with the characteristics of the buildings, the number of floors, the atrium, the fountain on top, etc. Like I said, there are some pretty good extant definitions out in the world for architecture. There's a really nice white paper by Martin Fowler called Who Needs an Architect that you can download from his website. And he points out a couple of things that he's harvested from the world in this paper. One of which is a post on the Extreme Programming mailing list that says, the architecture of a software system is its organization or structure of significant components interacting through interfaces, which is a pretty good technical definition of architecture. It's very close to my application architecture definition. Then Ralph Johnson, who's a really known software guy, says, in most successful software projects, the expert developers have a shared understanding of system design, and that shared understanding is called architecture, which is really another way of saying they have a vocabulary of idiomatic patterns of how things work in this system so that they can have very concise discussions about this architecture, which is a good social definition of architecture. But my second favorite definition of architecture is one by Martin Fowler, where he says, architecture is about the important stuff, whatever that is. Which sounds a little bit flippant, but it's true because different people care about different things. Enterprise architects care about different things than application architects do. And a lot of the job of architecture is to reconcile those two views because ultimately you have to work together to make something work. So it's about important stuff, and important stuff is different to different people. But my favorite definition of architecture is also a Martin Fowlerism, and that is it's the stuff that's hard to change later, with the caveat there should be as little of that stuff as possible. This to me is the real crux of the difference between architecture and design, because architecture forms the bottom layer of stuff. It's the things you build everything else on, and design sits on top of that. It's relatively easy to reshuffle the red boxes here because they're sitting at the top of the stack, whereas it's really hard to move the ones in the bottom because those are fundamental things that everything else sits on. So you can look at architectural elements. Your database is an architectural element because it's hard to change later. The web framework you're using is an architectural element because it's not trivial to change that. Within that framework, you can harvest idiomatic patterns about the way you use things within that framework. Those things are very easy to change and abstract and refactor, but the underlying framework is very difficult to change. Which leads me to some architectural considerations. The first of which is the politics of architecture. Most of the time, architects are the top-level IT person within an organization, which means they become the advocate of decisions made at the technical level, whether they want to be that advocate or not. And a lot of times, architects get embroiled in politics when they really don't want to be embroiled in politics, but it's just part of the job. And unfortunately, I can't help you with this. You need a good corporate-level psychologist to help you with this, but it is a reality of the world. Another thing that architects tend to encounter a lot, and this is particularly true in large enterprises, is this question of build versus buy. There's always pressure of, let's build a packaged piece of, buy a packaged piece of software or build it ourselves. But there's this kind of myth out in the world that is being promulgated by the sellers of a lot of this packaged software. And that is, you can buy this generic business process software, we just need to tweak it with just a few customizations, and it'll be exactly what you wanted it to be. What happens every time you hear this sentence and you sign a contract? Consultants start showing up, sometimes in buses. And then eventually a project manager will show up, because he's got the tie on, you see. This is mostly a myth, because not all business processes are commoditizable. Some of them are. Things like HR and finance are pretty commoditizable. But your core business is not commoditizable. If it was, then there would only be one other person in your entire field, because you could compete on price and everything else is just a commodity. We could have just 2 insurance companies in the world rather than hundreds of them. The reality is that businesses are radically unique even within the same problem domain. And the thing that this misses is that software can provide a strategic business advantage. And a lot of the reason that people get blinded by this is that a lot of the advances that we made by using software in the 90s and the early 2000s were replacing overhead with software processes. We've mostly mined that out, and now software is about strategic business advantage. And if you only think of software as overhead and your competitor thinks about it strategically, you will eventually lose, because they will be able to do stuff better than you can. And that really becomes the decision point of build versus buy. So I have a flow chart for this. First question you have to ask yourself, is this strategic or is it overhead? If it's strategic, you'd better build it yourself, because that becomes a competitive advantage in the marketplace for you. If it is, in fact, just overhead, you have to ask yourself, is it immediately functional without years of customization and extension? If it's not, you might want to think about building it. If it is, then you have to ask yourself, is it extensible in some sort of humane way? Is there an extensibility API? Do you have to go and hack things to be able to change it to do the things you want? Because those hacks never survive version upgrades. And so what happens is you buy this package, you hack it, and then now you're afraid to upgrade it because it'll break all your hacks, and you end up being 6 versions old, and then it stops being supported, and now you have to go and do this huge rework. If all those things are true, then you should buy it. Otherwise, you should build it. And this is going to be different for different companies. I do some consulting for a financial services company in New York, and one of their prime competitive advantages is they hire the best financial services consultants they can find. And they were thinking about buying an off-the-shelf HR piece of software, and I told them, that's crazy, because you are purposely putting yourself on a level playing field with your competitors when you could build a platform above what they have. And they ended up building their own HR software, and now they can do stuff in their hiring process that is impossible for their competitors who bought the off-the-shelf canned HR software. They got it sooner, but the company that I was talking to had a strategic advantage. The other thing you have to worry about is a phrase that I coined based on one of my coworkers called Dietzler's Law. For any framework or package X, 80% of what the user wants is fast and easy. The next 10% is possible but difficult, but that last 10% is impossible because you can't get away from the constraints of the package or the framework, and users annoyingly want 100% of what they want. The price of commodity software quickly approaches zero. There is no manufacturing cost for software. It's all in design, and once you have done the design, the price quickly approaches zero. And application server vendors got burned badly by this. Contrast this with SQL. There's an ANSI standard for SQL, but it's so weak it's useless. And so every database vendor builds their own extensions on top of it, meaning it becomes an architectural element. It's hard to move from one database server to the other because it'd be a huge amount of rework. The reason I bring this up here, this talk about architecture, is because of enterprise service buses, which tout being standards-based, but they're not standardized. They always talk about how standards-based they are, but they're held together with highly proprietary glue. Even the open source ones suffer from this because they're selling you training and consulting rather than bits. And this is not likely to change because most of the ESB vendors used to be application server vendors, and they realize what happens when software becomes a commodity. This is not to say you shouldn't use one of these, but consider the impact on your architecture, the stuff that's hard to change later. Once you get one of these in place and your entire enterprise is running on it, you're stuck with it. But you didn't build your own database server, so maybe you go into it with your eyes open, but that's a much more pervasive influence on your overall architecture than something like a database server. So I'm essentially out of time, but that's okay because I just have a couple of closing thoughts here about the things that I've been talking about. I believe, and I agree with Jack Reeves, that design is code. Other artifacts aid in creating code, but all artifacts besides code are transient. That is the final design. And you have to be careful using these really elaborate tools to help you with design because you end up with what I refer to as irrational artifact attachment. If it took you 2 hours to produce this beautiful diagram in Visio and somebody says that's not quite right, you're a little bit resistant to change it because you know how long it took to produce the original version. If it took you 3 days to build it, you're really resistant to change it because you are irrationally, emotionally attached to that artifact because you know how much work went into it. If you use whiteboard diagrams, they're nice because there's nothing there to get attached to because it's so easy to create and so easy to get rid of. And the last thing I'll leave you with is this idea of the last responsible moment. Not the last moment, the last responsible moment. Do I need to make this decision now? What can I do to allow me to defer this decision? And is there a way I can make it reversible? Let me give you an example of this. I was on a project that needed some asynchronous background behavior for this web application. This is a Ruby on Rails site. And the tech lead on that project very wisely said, you know what, we're just going to do a simple solution for now, and we'll come back later and address it if we need to. Fast forward 2 years, they have 3 distinct kind of asynchronous behaviors, and then they decided, okay, now we need to add a message bus to this application. But they knew exactly what they needed it for, so they were able to pick the simplest message bus that did what they know they needed to do in this application. If you're in a big design up front world, when the words asynchronous messaging comes up, you immediately say, oh, we need a message bus. But we don't know what we're going to need it for in the future, so we'll buy the biggest, most complicated one we can, just in case we need all that power, and you end up paying for that complexity from day one. If you can defer important decisions until the last responsible moment, you have a lot more facts to support making a really good decision, not an accidentally conservative one. Chris mentioned this book, 97 Things Every Architect Should Know, which is a collection of essays, and all the testing stuff was in my book, The Productive Programmer. And that's it.